Today, we're going to talk about endothermic and exothermic reactions in a little bit more depth. And we're going to take a look at how to represent endothermic and exothermic reactions in three different ways. In thermodynamics, we know that the world is divided into a system versus a surrounding. The system is the vessel in which the reaction is taking place. It would be the reactants and the container in which it is in, versus the surroundings, which would be like the environment and everything that exists outside of that. A system can be comprised of either an open system, a closed system, or an isolated system. As we have learned previously, an open system is one in which matter and energy can flow freely from system to surrounding and vice versa. A closed system is one in which only energy can flow freely, and an isolated system does not allow either matter or energy to come in and out of the system. Remember that with a reaction, we always have reactants on the left and products on the right. And what we must do in order for reaction to occur, we must break the reactant bonds so that the atoms can rearrange to form product bonds. In order for reactants to be broken, there has to be an input of energy. So in order to break reactant bonds, we must input a certain amount of energy, like we see in this little graphic here. And when product bonds are formed, there is an output of energy. So here's a little visual just to remind us. Energy input needed in order to break reactant bonds. And when new bonds are formed, there's always a release of energy. Okay. Now, what we're actually going to take a look at is, was there a greater input needed to break the reactant bonds compared to the output of energy that was released when the product bonds came together? The difference between those two will dictate whether a system is endothermic or exothermic. So the breaking of reactant bonds requires an input of energy, and making of new product bonds releases energy. Let's just say in total, there was an input of 1,000 kilojoules of energy needed, okay, in order to break these bonds. But when these new product bonds were formed, let's say there was 5,000 kilojoules of energy released. Well, if I had 5,000 released versus 1,000 input, there's a greater release compared to input needed. And so if there's a greater release, then this reaction would be exothermic. We've seen this visual in a previous slide. So in an exothermic reaction, we know that we will get an increase in surrounding temperature. There is a greater release of energy from the system to the surrounding compared to the energy that was absorbed initially. And in an endothermic reaction, what we've got is a greater input of energy that is needed compared to the output of energy from the system to the surrounding, and this would be indicated by way of a temperature decrease. So photosynthesis is a great example of an endothermic reaction that you should know. And you may know that in order for photosynthesis to take place in plants, you have CO2 that is required, as well as water and an input of energy, and this would come from the sunlight. And in the process, the plant would create glucose for itself, as well as oxygen, which is missing here because my video is covering that up. But you notice that energy is found on the left-hand side of the reaction, and this indicates that the process is an endothermic process. So if more energy is needed to break the reactant bonds compared to the output of energy that is released in the new product bonds, we would say that the overall reaction is endothermic. And here is the same thing, just worded slightly differently. So more energy is needed from the surroundings to be inputted to the system compared to the amount of energy released from the system to the surroundings. Okay, so a very common example of an endothermic reaction would be a chemical cold pack. In a chemical cold pack, you have a plastic bag, and within that plastic bag, you have another smaller bag that contains the water, and then you also have some of the crystals of ammonium nitrate. And when you break the two together, so the water is released, the ammonium nitrate crystals will start to dissolve. Now, the enthalpy of dissolution, so the dissolving of the ammonium nitrate, will cause that ionic salt to break into its respective ions. And in that process, we notice that the temperature drops, hence it is a chemical cold pack. And so this particular salt, the dissolving of this salt, is an endothermic process. And again, you would notice that the energy value for this dissolution would be written on the left-hand side. So there's the ionic salt, when dissolved in water, produces the two respective ions. There are some salts that will yield an exothermic reaction, and those would maybe be appropriate for a hot pack. Exothermic reactions involve the output of heat energy, and you would notice an increase in temperature, and all combustion reactions would fall into this category. So if more energy is released in the making of new product bonds compared to the amount of energy needed to break the original reactant bonds, we would say that the reaction is exothermic. Another good example of this reaction would be the combustion of hydrogen. So we've got hydrogen gas plus oxygen gas yielding water, and we notice that we get an output of energy. So the combustion of that, obviously you're thinking, oh, water, liquid, but because this is a highly exothermic reaction, this would vaporize into a gas, and you would get a huge amount of energy released. So notice energy is on the right-hand side of the equation when it's exothermic. Okay, so ways to represent endothermic versus exothermic reactions. Notice in method number 1, we have the actual energy value written as part of the equation. So if it's endothermic, the energy associated with that reaction, if it's written on the left-hand side, we would say that it is endothermic. If it's written on the right-hand side, then it would be an exothermic reaction. Another way to denote whether something is endothermic or exothermic is you would see that there's an enthalpy value that is written to the right-hand side of the equation. So this is the same as above. The only difference is written to the right. And you notice that this positive value indicates that it is an endothermic reaction. And if it is a negative value, like we see here, the negative indicates that it's exothermic. Okay, so exothermic means that you would have a greater output of energy compared to input, and it would be written on the right-hand side, or if it was written off to the side as a separate enthalpy value, you must put a negative to indicate that it is exothermic. The last way we can show endothermic or exothermic is by way of energy level diagrams. So an energy level diagram shows energy stored in the reactants compared to the energy stored in the products. So let's take a look at this scenario here. Here you have H2 plus Cl2, so HH bond and a Cl-Cl bond. And what we're going to do is we're going to make 2 molecules of hydrogen chloride. So H2 plus Cl2 yielding 2 HCl. In order for this reaction to occur, there must be bonds broken for the reactants. So there has to be a certain input of energy. This input of energy is also known as the activation energy. So the activation energy is the minimum amount of energy needed in order to form the products. So what we notice here on the y-axis is you have potential energy here. So we input a certain amount of energy, and we have now broken the reactant bonds. We notice that when these bonds reform and come back together, we get a certain output. And I notice that the output arrow, okay, is greater than the input arrow. So because we get a greater output of energy, okay, in the formation of these 2 new product bonds, we would say that the overall reaction is going to be exothermic. Output is greater than the input. And so the difference between these 2 plateaus, the difference between the potential energy of the reactant bonds compared to the product bonds, okay, we notice that this is sort of like a downward slope here. It would yield an enthalpy value that is negative, so meaning an exothermic reaction. The way that you would show this as a general diagram is we have this plateau here showing the reactants. We would have a certain input of energy, okay, until we reach the top called the transition state or the activated complex. And then what we would notice is we would have a downward until we reach the plateau of the products. Now, notice in this case, the input of energy is greater than the output. Okay, and so here we would have what is referred to as an endothermic process. So we would have an upward point where your delta H, your enthalpy value, would be positive. Okay, and here again is showing an example of an exothermic. So the input is smaller than the output. The output always goes from the top all the way to the bottom, and so that arrow is a lot greater. Okay, now we're going to learn later on how catalysts affect the rate of a reaction, and catalysts also lower the activation energy. But again, we'll learn that a little bit later on. Okay, so here's a summary of what a general energy level diagram would look like. Y-axis is potential energy, x-axis is the reaction pathway or the reaction progress. You would need to show the reactant line, the product line, as well as an activation energy. And what you'd want to show if it is exothermic, that this output, so the product line would be lower than the reactant line, so the potential energy of the products is less, whereas with an endothermic, the reactants have lower potential energy compared to the products.